Matthew Schmidt, and I'd like to welcome you to Genetics. In this session, we're going to see how we can use recombination data to construct a genetic map, and we'll do a lot of permutations and variations of that type of analysis. So linkage and gene mapping. By the way, the video that's very previous to this one is very important in understanding the whole idea of crossing over and what it does to genetic data and what it means. So if you haven't watched that yet, it really is necessary to watch that one first before we do this one. So this type of idea and this type of a problem almost always comes up in some way or another. So I can't stress the importance of it enough. It's a little bit lengthy. It can be intimidating seeming at first, but believe me, if you do it exactly the way I ask of you, I beg you, everything will be okay. Let's take a look at an actual cross in Drosophila, and let's set the stage for what we're doing here. So we're going to do a cross in what has come to be known the traditional fashion, where we take two pure breeding parents, get a doubly heterozygous F1. As we saw last time, we're then going to do a test cross and look at the types that exist in the offspring. All right. Now this cross is in Drosophila, and we're looking at two linked genes that happen to be linked on the X chromosome. Really, it doesn't matter. The same principles apply to linkage on any chromosome, but there are some advantages to using the X, and you'll often see the X chromosome in these type of problems. One of the reasons why is because this is the male over here. So this symbol here is what we use to denote the Y chromosome. Remember, even though things aren't the same exactly in Drosophila and humans, one thing that is the same is that the Y chromosome really doesn't have a lot of genes on it, certainly not the same ones that are on the X chromosome. So crossing over could never ever occur in a male with respect to the X and Y. Even though they're a homologous pair, they can never cross over. So the bottom line is we know what gametes we're getting from this father. Let's take a look at the mother as well. There's two ways to look at this. So she's pure breeding for these two traits, white eyes and miniature body. These are recessive traits, so she's little w, so she's white-eyed. And she's little m, which is a miniature, a small body size. But remember, now that we're thinking of them as linked, we're drawing that line that represents the chromosome, in this case the X chromosome. So remember again also, if a crossover did occur in between those two loci, it doesn't matter in a pure breeding parent because there's just nothing else. You could try and mix this up as much as you want, but we're always going to know what gamete is going to be able to be produced by this parent. The bottom line is, so we're crossing a white miniature female over here with a red-eyed normal male. Remember, we used that term hemizygous for males with respect to genes located on the X chromosome because he only has one copy, right? He's W+, which is the wild type red-eyed color, and he's M+, which just all you can say about that really is his body type is normal. It's not miniature. Now really what's going to happen in the F1 is this whole entire chromosome right here, we know that we're looking at only the females, by the way, in this case, and you'll see why in a moment. But to make a female, an X chromosome has to come from the mother, right? And an X chromosome has to come from the father. And there's no other possibilities except for those two. The chromosomes move as one, right? So if we looked at it this way, the F1 is heterozygous at both loci, right? Phenotypically, it's red-eyed, and it's got a normal body shape and size because of the dominance of those wild-type alleles, right? But here's where it gets interesting and what the point of this really is. So we're going to do a test cross here, and remember what a test cross is. You're crossing someone by someone who's totally recessive, and in this case it's a male who only has one X chromosome, so this is a white and miniature looking male. But the bottom line is, I hope you can see why we're doing this. No crossing over can occur between the X and the Y chromosome. Even though they're a homologous pair, it's not going on. And I might as well just say it. For reasons we don't have to go into right now, crossing over never occurs in males at all in Drosophila. So that's just something to tuck in the back of your head. But for now, my point is this. We can now look at all of the offspring, whether they be female or male. Because if they're male, they're getting this Y chromosome from their father, which is not contributing anything that has anything to do with W or M. If they're females, they're getting this chromosome from their father, and no matter what, it's little w, little m. It's not going to contribute to the phenotype. I mean, you need it, but what's going on over here in this parent is really going to determine what the phenotypes are going to be, because we know what we're crossing, what the gametes produced by that F1 female who's going to be a mother. We know that what's going on in there, we know what it's going to mix with, if you will, either this or that. So basically, let's think about what would happen in this situation if no crossovers ever occurred, right? What would happen? So let me erase just because this is getting a little busy. If we just did this cross and a crossover did not occur at all of the offspring would look parental, right? Because this entire chromosome would go into the offspring, and whichever one of these two that it mixed with, it really wouldn't matter. One set of the offspring would be white and miniature, right? And if this chromosome was the one that went, they would all look red and normal. And as you see over here, that's why we refer to those offspring as the parental types. They resemble one of the parents. When you do it this way, that usually means the original parents from the P generation, right? This one resembles that father. This one resembles that mother. A recombinant offspring could not be produced in this case. Just to recap, remember, usually independent assortment is what creates the recombinants. When the genes are linked, only crossing over can create the recombinants. So I just said if there's no crossing over, there's no recombinants, and you'd only see the parental types. But now, very importantly, let's find out what would happen if a crossover does in fact occur in between those two loci, okay? So I'll just draw that as an X, and we can see what type of, how the chromosome will be rearranged. So following along in red, we're going to get one chromosome that now has W with M plus together. Remember what's happening. I'm drawing it. This is the convention and the best way to do it. But the chromosomes are both getting cut and rejoined to the other one. All right? And then we'll get also on the bottom, and if one happens, the other has to happen, the W plus with the M, right? I believe I animated that. It's probably going to ruin my drawing, but you can see there. And look what I did. I used the different color. I'm going to fix that. Just, I know you get it, but if there's a crossover there, we'll keep this in blue, the W and the M plus, and we'll keep this in red, the W plus and the M. But think about it. So now, if what we've now called this red chromosome it ends up in the offspring, we're going to have someone, a fly, who looks wild type, so red-eyed, but miniature, right? And that's this class right down here, a recombinant class. And the other recombinant class is what we've drawn in blue here. It's going to be white-eyed, but normal body size, right? Right here. So those are the two recombinant classes. Now, if you see this data, this is what it basically means. We had said last time that pretty much always in this type of situation, you'll see more of the parental types than the recombinants because probably crossing over doesn't occur all of the time, right? And if you know the genes are linked, then you're going to see recombinants a certain amount of the time when a crossover does occur. But now we want to really ask the question, so how can we use this data to actually determine, to map these genes? And in this case, what mapping really means is to determine how far apart the W locus is from the M miniature locus. How far apart are they? So how could we do that? Well, it turns out, I don't want to get anyone angry by saying that it's easy. It's not easy, but it's not complicated once you understand it. So the same data we just had, I kept on here above the red line because I want you to see how you can use it. Basically, this is the way we want to think of it conceptually. Just forget about the numbers for 1 second. If two genes are very, very close together on the same chromosome, I think we said this last time, doesn't it make sense to you guys that it'll be a lot less likely for a crossover event to occur between them? And as they get further and further and further apart, it'll be much more likely for a crossover event to happen in between them, right? So generally speaking, the further apart they are, the more crossing over is going to occur. That's the conceptual part. The more mathematical part is to say, look, these parentals, those are offspring that resulted when a crossover did not occur, right? The recombinants all came from a situation where a crossover did occur. So the math of this is, as I said, is pretty straightforward. And what that means is we've got to ask ourselves this question. How many of the offspring are recombinant? Because the number of those is going to tell us how frequently a recombination event occurred between these two loci, and then subsequently that gives us an exact idea of how far apart those things are. So what are the numbers of recombinants? There were 455 of one type and 445 of another type. The numbers will usually be similar but not identical, and it's really for the same reason, that if you had a 3-to-1 ratio like in the past, if you looked at offspring, you wouldn't necessarily get exactly like 600 and 200. You might get 611 and 180, whatever makes the math work out right. The reason is because we're looking at a sampling of a large amount of gametes. So don't worry about that, but realize that these all came from recombination events. So what we just have to do, and you can have a calculator handy if you want to. I sort of cheated by doing the math beforehand. Usually you are allowed a calculator on an exam in this situation. So 455 plus 445, the grand total equals 900. So out of the total of 2,441 fly offspring, 900 of them were recombinant. And simply what that means is if we divide the 900 recombinants over the total number of offspring, we get a percentage. It's 37% or 0.37. What that means is that 30% of the offspring are recombinant. But what it means to us in this context is that 37% of the time a crossover event occurs between these two loci. And that's the information we need to make the map. So based on that so-called recombination frequency, we build a map, and by definition they said that, look, for every 1% crossing over, we're going to name that a map unit. Okay? So this term MU, it's an actual term, map unit. We'll talk about this in a second, but they were careful. They're not saying that this is equal to a very specific actual distance. It's a map unit defined by 1% crossing over. 2% is 2 map units, 3%, 3, etc., etc. So if you see 37% crossing over like we just did, that means that these loci are separated by 37 map units. Okay, a map unit is considered to be similar to a physical distance. Now this may not seem like a fancy map, it's just a line, but that line represents the chromosome. And what it's saying is that the W and the M loci are 37 map units apart, if you want to think of it that way. Another term, depending on your book or your professor, that you probably should know is the term centimorgans, which should never be confused with centimeters. A centimorgan is paying homage to the one of the most famous fly geneticists that ever existed, which was Dr. Morgan. So a centimorgan equals a map unit. It's the exact same thing. Unfortunately, sometimes they'll use one and sometimes they'll use the other. So a cm in this context, again, it is a distance or akin to a distance. All right. Bottom line, guys, the percent of recombinants divided by the total gives you the percent recombination, and that correlates with a map unit or centimorgan distance. Okay? It's not really that bad. If these genes were unlinked, you would see about the same number. Remember last time we said you expect a 1-to-1 to 1-to-1 ratio? We're not seeing that now, but we're seeing a fair amount of recombination, 37% in fact. Okay? Now, from a more philosophical point of view, well, actually, before we get to philosophy, a couple of observations about the map. So I think you get this, but what I'm saying in the first line here, is if the genes had been closer together than 37 centimorgans, we would have seen less crossing over. If they were further apart, we would have seen more crossing over, right? But here's a very interesting thing to keep in mind for now, but especially also for something that we're going to do in a minute. Double crossovers also can occur. Now, double crossovers, this is very important. They reduce the apparent map distance. You'll see what that means in a second, but this is an important take-home message. Calculated distances, even the way we just calculated them, are always more accurate and more reliable the shorter they are. The closer together two loci are, that's the more reliable number. Why? And the reason is because double crossovers eliminate recombinants. They don't really, but they eliminate our ability to see them. So when I say double crossover, this is what I mean. Here's our same situation with the W and the M locus in a heterozygote, right? We made the situation where a crossover occurred between them. But there's no reason in this world, especially as things get further and further apart, that two crossovers could not occur. There's no reason that couldn't happen in between the same two loci. Let's see what would happen if that actually occurred. I want to make sure I draw it in the right colors this time. So there are my two X's. I'll erase the ones that I drew since these are so much more official. Let's follow along in red. What would happen? So we're going along, there's one crossover and then another. Look what happens. For all purposes, what you end up with still has W plus and M plus. Where you should be counting two crossover events, the offspring that you're going to see look just like the original, look like the parentals. The two crossovers, one of them created a recombinant gamete, but then the second one flipped it back so that you can't tell. And the same goes for the other one, which we could draw in blue, where we now have, we start out with little w, little m, and because of the two crossovers in that interval, now we're still seeing that. So whenever you make a calculation based on the recombination frequency, you are not able to take into account the double crossovers. Therefore, you're underestimating the true distance. You're doing it based on a certain number of single crossovers. You're not able to get the double crossovers. So the phenomenon of double crossing over reduces the apparent map distance. Okay? When we do a problem, when we do our next problem, you'll see exactly how this pans out into reality. But I'm sorry, I don't want to be redundant, but I think I can say it better, and just to make sure we're clear about this. In this situation that we just saw, two crossover events happened. And if you analyze the offspring coming from this, you wouldn't see any of them. So you wouldn't be able to take that into account, and you would end up estimating a shorter map distance than was actually the case. Another really important thing, this cannot be overstated. Any genes that are located more than 50 centimorgans apart whatever a centimorgan is in terms of actual difference, they appear completely unlinked. This is so important. And for genetic purposes, they may as well be unlinked. Because think of what's been going on. We said 1 map unit, 1% recombination, great. 10, 20, 30, 40. At 50 map units, by definition, you should see 50% recombination, right? What if you get bigger than that? Say two things were 80 map units apart, which is possible. Would you see 80% recombination? You wouldn't, and you couldn't, because you have to go back to the last lecture if you really want to make sure you understand this. But 50% recombination is the absolute maximum that you can possibly see no matter what, whether it's through independent assortment or whether it's through crossing over. So that's why once two things are more than 50 apart, you're not going to be able to tell it. In essence, guys, so many crossover events are happening between these loci that they're acting as if they're not linked anymore. And that's one of the reasons why we often say that when things are relatively close together on a chromosome, that's when you observe the effects of linkage. Okay? I hope that makes sense. But it also sort of limits our ability to make maps. So what that means is often we're going to have to do is say, okay, whoops, I didn't want to draw that. Say, okay, here's our chromosome. Here's locus A, and we know that that's 25 away from B. And say we do an independent thing, and we know that B and C are 20 apart. Then we do another one, and we know that these are 30 apart. You have to have numbers under 50. But by extension, we could then add them up and say, okay, if we want to know the distance between A and D, in fact, it is 75. But if you just used A and D in your analysis, you would never see more than 50% crossing over. So that's sort of an extension of the idea that smaller distances are always better and more reliable and more accurate. Now this is a sort of a philosophical point. Genetics and cytology, remember, genetics deals with the information, cytology deals with looking at the chromosomes and seeing what's going on there. So as I say here, there's a strong implication that the map distance does in fact correlate with a true physical distance on a chromosome. I don't know what it could be. I'm making it up. A nanometer. I have no idea. That's probably totally incorrect. But that it does correspond with some literal distance because a chromosome is a physical entity, right? But just realize this. Maps are constructed from genetic analysis, and there could be other interpretations. I'll give you one idea in a minute. It turns out it seems to pretty much be true that the information we get about distance from recombination data, there are ways of doing this. It does seem to correlate with true physical distance. So to the extent it is true, this is another example of the way genetics and cytology reinforce each other, which is always good. We don't want them to contradict each other. Technically, linked genes are referred to as linkage groups. And you guys, a linkage group in essence is a chromosome or a part of a chromosome that we have information about, right? So in cytology, the physical structure is the chromosome. The linkage group is a representation of the gene's place on a chromosome based on recombination data. But on the other hand, so that's all good. On the other hand, though, let's think about something that could happen that would not make a linkage group, I should say, would not allow you to say that there's a direct correlation between map units and physical distance. Because one thing that's, sort of being assumed here, but it may or may not be true, is that crossovers occur completely randomly at any place on the chromosome. It has been discovered that there are certain places that are called hotspots for crossing over, where more crossing over, for whatever reason, occurs in this region than it does in that region. You can see how that would affect this idea that a map unit's simply a definite distance and that's it. So we don't want to take it too much further than that. All other things equal, it's a good idea to think in your mind, where else would you do it, to think, that the map unit is pretty much like a physical distance. Okay? All right. Now we come to something that I can't say a lot of people are thrilled about it. It's a situation that leads to a problem, called the 3-point test cross. All right. Now, I don't certainly want to jinx it by saying that this is really hard. In fact, if you do it the way I'm going to propose to you, it won't be hard at all, I hope. But the reason I want to say this is a lot of people, when they see this, they start to panic. They say, there's all data all over the place. I don't know what's going on. The worst thing you can do, aside from never studying and blowing off class, when you're confronted with a genetics problem, is to panic and just start doing random things. Setting it up is really often the key to the whole thing. So if you say, go in with confidence and say, I understand how this thing works, don't panic and follow the methodology. It's not so bad. It's just, I've seen, unfortunately, people really go off on little tangents and totally screw this up, even if they basically understood the idea. So it's really, look, the good news is the idea of this is pretty much the same as what we just did. We're trying to construct a genetic map, but we're doing it keeping track of 3 genes at the same time instead of 2. This makes it a little bit more complicated, but it also allows us to construct a map with 3 loci and their relative positions, which is a great thing to do. So it doesn't always happen this way, but look, it's hard enough, so I want to present it in a streamlined way, and I'll have some things to say about if it's not presented that way later, how you can sort of make it more like this. But what I mean is this. So generally speaking, don't always assume this, but unless you're told otherwise, this is often the way it is. That all the mutants are recessive number 1, and often the genes are X-linked. It really doesn't matter the X linkage, but if it is, remember that, when you draw it out, the father has a Y chromosome instead of a regular homolog, all right? So here's 3 loci that happen to be, again, on the X chromosome that we're going to use. These are common ones you might even see in a problem. And they're called scute, echinus, and cross-veinless. It doesn't even matter that much what the phenotypes are for these. I'll just briefly mention them. SC plus, and all of them plus really, mean normal. So what's normal? Well, scute means that there's a loss or lack of bristles on the thorax of the fly. Usually there are these little hair-like projections. In the case of a scute individual, they don't have that. All right? If you're wild type, you're normal, meaning you do have that. Remember, in fly genetics, they name the loci after the mutations. Echinus is so-called rough eyes. It's hard to describe what rough eyes mean, but you can see it, especially under a dissecting microscope. If you're normal, you don't have rough eyes. CV is cross-veinless. That's a little easier to understand because the wings of flies have veins and they have cross veins. Well, if you're cross-veinless, you don't have those type of veins on your wings. All right? And if you're normal, you do. So we have 3 loci where we have the normal version and a recessive mutation. All right? Now, when I say these crosses are always done in the same way, there are a lot of ways you can do things, but this type of analysis it can only be done if certain conditions are met, and that means you should be used to this. Start with true breeding lines, get the F1 females, test cross them, and analyze the data. Remember, since crossing over doesn't occur in males, whenever we do this, the female F1 parent is really generating all the diversity in the gametes. Okay? So far, so good? No one's panicking yet. Good. All right, so here's the thing. I know this may look daunting or it may look fine. I don't know. We're going to draw it out just like we did last time. Now, you have to draw it in some way, or if it's presented to you, we have to write it in some way. But I got to tell you, no gene order is necessarily implied. I wrote it this way with scute, echinus, and cross-veinless, echinus in the middle. It may or may not be true, but you'll find out if you do it the way I'm begging you to do it. Because if you do it this way, it's hard to go wrong. So look at the parents. This one, you can tell it's a female even though we didn't write it because she has 2 X chromosomes. And she's mutant in phenotype at all 3 locations. She's scute, echinus, and cross-veinless because she's doubly recessive for those mutations. And that means she's also pure breeding, and it means that any crossovers that happen in her are irrelevant. That's why it has to start this way. The male she's being crossed with is pure breeding wild type, right? He's always plus plus plus, and he can only donate, no matter what happens, plus 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 to his daughters, right? So based on the idea, we don't want to make this overly too complicated, because I hope you can see that for the daughters, this chromosome comes all together, which has the 3 mutants on it, and this one comes from the father, which has the 3 wild types on it. So this F1, as I suspect you would guess, is heterozygous for all 3 of these loci. Phenotypically, it looks normal, normal, normal because of the dominance of the normal over the recessive mutant alleles, right? But then we're going to do a test cross with, you know what a test cross is, with a male who's triply mutant. Remember what that means. Not only can no crossing over occur there, but his gametes, while necessary to form an offspring, are not going to really contribute to or determine the phenotype. Only what goes on over in this female fly, the mother over here, only that is going to determine what the offspring look like. Now, I've written this data out in the way that it needs to be written out. So for now, let's just assume that this is what you're given, and we'll do it this way. If in fact they don't give it to you this way, you're going to want to rearrange it, but don't worry about that right now. Let's just understand how to do the cross, okay? So it shouldn't be too shocking for you guys, and I'm serious about that, to realize that if no crossing over occurs at all, period, you're going to get offspring that all look like the parental, right? Because this chromosome will go and mix with whatever it mixes with over here, which won't really matter, or this chromosome will go. So these two right here, skewed echinus and cross-veinless, and plus, plus, and plus, are the 2 parental classes. And you'll notice that they are present in a greater number, a much greater number than the others. So this is not really a different concept than we were thinking about. I think you get this, but I just want to be clear. I actually drew an almost straight line. My point is, so this whole column is referring to skewed. If I just write plus underneath there, it really means SC plus, okay? It's just the easiest way to keep track of it. I don't think you should be writing SC plus. But just put them in columns that are reasonably, straight. And that way we can just go down the column and say skewed, wild type, etc. All right? Now, so I think it's clear that both of these are parental, right? So let's just check out what would happen if crossovers occurred. So, we're doing the problem, but we're really not solving it. We're doing a hybrid of solving it and seeing what happens. Once you understand, you'll feel so good. I'm erasing this over here because I want to ask you and me and ourselves, what will happen if a single crossover occurs in between the scute and echinus loci? Well, let's see. Doing our regular convention, we'll do one in red there. We're going to make, if a crossover occurs there, we're going to make 2 sort of mirror image types of gametes, right? One is going to be, I'm going to keep my colors, right? One is going to be skewed, normal, normal, right? That's a recombinant. Can we find that down below? Skewed, normal, normal? We can. It's right here, right? Skewed, normal, normal. The other one that's made by the same crossover event is plus echinus and cross-veinless. And that is right here. So these 2 come about when that crossover occurs between skewed and echinus, and that's why they are one of the recombinant classes. They're a new combination of these 3 traits that was never seen in the parent before, right? Okay. Same idea. I'm going to erase it. Ask yourself what's going to happen if a crossover event occurs between EC and CV. we're going to get one chromosome that looks skewed, echinus, and plus. Do we see that down here? Yes, we do. You see how I arranged the data so it'll be right one after another in a line. The corresponding other one that's going to be made there is plus, plus, and CV, and that's right here. So these guys are another recombinant class. They're different from each other, but they're recombinants because they do represent another combination of the three that was not seen in the parents before. Okay? And now here's another interesting thing. What if a double crossover occurred? Now when I say double now, I mean something a tiny bit different than what we said before. What I mean is there's a certain chance a crossover is going to occur in between skewed and echinus. There's a certain probability one's going to happen between echinus and cross-veinless. But who's to say that one can happen in both of the intervals at the same time? It can happen. That's a double crossover. Now what will happen if this double crossover occurs? Check it out. We will now get skewed plus cross-veinless. You can see that right there. And the other one we'll get from that same event is plus echinus and plus, which you can see there. Those are in low frequency because double crossovers happen a lot less frequently than a single crossover does. So that's a double recombinant class. So this data, that's the analysis of this whole cross and this data and why it works out the way that it does. We didn't get to the map quite yet, but we're going to see how we can put this all together. But for now, realize it does look, there's a little strangeness going on in here, but generally speaking, the parentals will always be the highest number, right? The double crossovers will always be the lowest number. It depends on the exact location of the other loci. Here, you see 163 and 30 and 192 and 148. Those are numbers that are fairly similar, and often they won't be that mean, and they'll give you two classes which you can clearly see belong together. But here, as long as if you do the way I did and you say, what would happen if a crossover occurred here? Those two have to come from the same crossover event. These two and these two, even though the numbers don't 100% tell you that. All right? If you need a pause or go back and look at this, that's fine. But we're going to go ahead and see, now that we have this data, how do we go ahead and put it onto a map or construct a map with it? So I had just animated the same thing that I drew, but I drew it even better, so don't worry about it. Okay, so certain terminology that's going to be important for the construction of the map is cis and trans. Now, you may know this from chemistry or somewhere else. If mutants are on the same chromosome, they're said to be in the cis configuration. So let me draw you a little picture just using any two loci. Here's mutant A and B and plus and plus. This is considered to be cis. Cis sort of means next to, right? The two mutants are on the same chromosome, the two wild types are on a different chromosome. The trans configuration would be like this. It's sort of as if that doesn't represent a crossover. I'm just saying they're not next to each other, they're across from each other, the two mutants and the two wild types. From a purely genetic perspective, you guys, both of these organisms they're going to exhibit the same traits. They're both heterozygous A+, right? So the only time this is important is when you're doing an analysis of recombination. So know what cis means and trans mean, because we're going to use that very, very importantly in our analysis of how to make the map. Okay, cis and trans. Now, try again to make an almost straight line. This data up here, that's the exact same data that was just on the other page. But now we want to use it to make the map. Now, just for the record, sometimes they'll just say, without even telling you the cross, they'll just say, hey, look, here's the data. Go ahead and make a map. And then you're going to have to make certain assumptions about it. For example, that the parentals are the most number, the double recombinants are the smallest number, and you'll have to figure out which recombinant classes are which. But we know, since we just got this data. So guys, it's not hard, I promise you. Let's just take it easy and let's see what's going on here. What you have to do, I command you to do it this way. Even though there are 3 loci here, you have to consider them in pairs. And we're going to get the map distance between pairs. Then we're going to put it all together, okay? So the first pair we want to look at are scute and echinus. What that literally means, you guys, is we want to forget about cross-veinless. I'm getting rid of it. Don't want to hear anything about cross-veinless. It's easier for me because I can erase and put it down there. If this is on a piece of paper, sometimes a good strategy, if you have something you can use, is just to cover up that, column, because you don't need it for this part, but you're going to need it later. So guys, here's the whole key to this. I want to know the map distance between scute and echinus. We can do it the same way that we did the original simple map between 2 loci, but we want to use the cis and trans terminology. So in the parents, it doesn't always have to be this way, but in this case, scute and echinus are on the same chromosome, and plus are on the same chromosome. Is that a cis or a trans arrangement? That is, in fact, a cis arrangement, right? So here's the deal, guys. We want to count recombinants. Isn't that how you make a map? The amount of recombinants over the amount total. Who are going to be recombinants? Well, since the parents are in cis, we're only looking for those offspring that have scute and echinus in trans. Those are recombinant. Anyone else is parental with respect to these 2 genes. So let's look at these next guys. You could look at them one at a time. We happen to have arranged them in a way that the classes are together. If they weren't, it doesn't matter. Let's look at each one of these. SC and plus, is that cis or trans? That's trans. I'll just write T. Let's just go down the list, then we'll add them up. That's not a plus, that's a T, by the way. Plus and EC, trans, right? What about this? Scute and echinus. Doesn't that just look like the parent? So that's cis. Plus plus, cis. SC plus, trans, and EC plus, trans. So I'm going to circle the ones that are in trans in red and their corresponding numbers. Now I just made a little mistake, but I just fixed it. We're only interested in the ones that are in trans, right? And there are 4 groups of them. So all we got to do is look down here. SC and EC, I want to know the map distance between the 2. I'm going to count up the recombinants. So it's 163 from here, 130 from there, 4 from there, and 6 from there. Add them all up. So if you have your calculator out, again, I cheated by doing the math in advance, you get that 303 out of the grand total of 3,256 are recombinant. We can calculate a map distance from that, because if you do the math, you'll find that 9.3%, that represents 9.3% of the offspring, which means that those 2 loci are 9.3 map units apart. Now, if really we were doing it just like before, we just make a little diagram. We'd say SC is here, echinus is over here, and they're separated by 9.3 map units, right? That would be that. Now, obviously, we're doing it more detailed, but that's all it's saying right now. So you write that down, you keep it in the back of your mind, or even in the front. But then you say, all right, next pair number 2. So to do that, I've got to erase all this stuff, because the next, it doesn't really matter what order you do it in, but it's good to get used to a certain way. So the way I do it is to take, I started with the first and the second one. Now I'm going to keep scute, and I'm going to compare scute and cross-veinless. That means I don't care about echinus anymore right now. Go away, echinus. It's always harder to cover up the middle one if you're literally trying to use a piece of paper or something. But it doesn't matter. All we care about is scute and cross-veinless now. Now again, the way I did it, it turns out that all of the parentals are cis for any of the combinations. It doesn't have to be that way though. Whatever they present you with, you have to compare what's different from the way the parent was. So the parents were cis here for scute and cross-veinless as well. So let's go down the line. Here we see SC and plus. That's trans, right? plus and CV. That's trans. But SC and plus, oh, that is also trans. Plus and CV, also trans. But these bottom ones, SC and CV, that looks just like the parent, right? Because it's in cis. And plus looks like the parent. We just do the same thing. It gets almost mechanical. And if you're bored, I'm being serious about this. If you find this to start getting tedious and boring, almost that's a good thing, because if you're bored, it usually means you understand it. If you're freaking out and you're crying, then it's better to be bored. My point is, you just keep doing it. So if I want to know about the distance between skewed and cross-veinless, I got to count the recombinants, those that were in trans, with respect to those two. And you'll see that there are 4 classes there. So I add up 163, 130, 192, and 148. And you get your handy calculator. You'll find that that represents 633 out of the total of 3,256 offspring. And that's 19.4% or 19.4 map units. So again, I think you've got this by now, but if we just wanted to draw the map of skewed and cross-veinless, we draw it and say they're 19.4 map units apart. Now we just got to do the same thing for echinus and cross-veinless. And we'll almost be done. Not quite. So what do we want to get rid of? We're not interested in skewed for this part, right? Go away, skewed. Echinus and cross-veinless, again, it doesn't have to be this way, but our parents were cis for these. We're looking for trans. Cis, cis. I hope you can see all the rest of them are the trans type, right? So with respect to echinus and cross-veinless, this, and this will all be recombinant types for those 2 loci. So we add them up, 192, 148, 4, and 6. And if you do that, you'll find that there are 350 out of your grand total of 3,256, which is equivalent to 10.7% recombination, or by definition, 10.7 map units or centimorgans. And you probably don't even want me to do it, but if you just made a map of EC and cross-veinless, they'd be 10.7 map units apart. Right? So the question is, how do we put it all together? Now, you've got all this information. This is the 3 map distances that you've calculated. When there are 3 loci, there are also 3 pairs that you can get information about, right? And we've done that, but just to be very clear conceptually about it, you do the first and the second, the first and the third, and the second and the third. That's the only pairs there are here, right? So the big question when you draw the map, again, I drew it so that it turns out that this is in fact the correct order, but it might not have been. The way to find out is you've got to ask yourself, which gene is in the middle? That's the central question to drawing the map after you've done all the calculations. Which is in the middle? Think of this logic. Whichever 2 are the farthest apart, the other one has to be in the middle, right? Which ones are the furthest apart? Is it not these 2 that are 19.4 map units apart? So that's skewed and cross-veinless. That means, you guys, they have to be at the edges, and echinus has to be in the middle. Now, it really doesn't matter. You know, you could switch this around. That really doesn't matter. All you have to know is which one is in the middle. Okay? And then you just fill in the distances, because between skewed and echinus, you decided there's 9.3 map units there. Between echinus and cross-veinless, you said that there are 10.7. And then between skewed and cross-veinless, you said that there were 19.4. That's wonderful. It's awesome. You may notice, and if you get it and you're good with it, take a little moment to celebrate. You may notice one little weird thing, though, and that's the following. If you add up the map distances here and here, 9.3 plus 10.7 do not in fact equal 19.4, they equal 20, right? So what's up with that? This is the correct way to do the map, but remember, we said something about double crossovers causing us to underestimate a map distance, and furthermore, we also said that calculated distances that are smaller or loci that are closer together are more reliable, right? So let's take a look at this. If we want, and they often will say this, calculate the most accurate distance between SC and CV, the ones on the ends here. The farther two genes are apart, the less accurate is the calculated distance because of the fact that double crossovers occur in there, and that we saw some double crossovers, but when we're doing it as the pair, we just calculated between skewed and cross-veinless. It means that this 19.4 is likely to be an underestimate, and therefore it's quite appropriate and you should do it. When you have information about smaller intervals, add them up. So if you get 9.3 and 10.7, put them together, it is better to say that even though I calculated 19.4 map units between skewed and cross-veinless, 20 map units is a more accurate distance. It's always going to be a larger number because you've missed out on some of the crossovers because of those doubles, okay? So be careful of that. If they ask for most accurate, you always want to add up shorter intervals than go with the calculated value if you're able to do that, if you have that information, okay? Excellent. So I think we've said some of these things, but let's just make sure. Data trends. The largest classes always represent the parental. The smallest classes always represent the double crossovers. That's in case they don't tell you, and it's no other way to find out. Sometimes you're under time pressure as well, right? So that's a good general rule. With respect to skewed and cross-veinless, so in our case, these were the furthest apart. Remember that when I say these, I mean double crossovers do regenerate the parentals, and that's why we ended up underestimating the true number, which is why we said let's add up the smaller intervals and get a more accurate distance. Okay? Definitely in the problem solving, you're going to want to practice with some of these. We'll see them in some different, types of ways that can be presented to you, etc. But if you understand it, you should be able to be successful with these type of problems. So, problems and tricks. And when I mean problems, I mean what can go wrong and what are some quick tricks you can do to fix it. So, here's one thing. In a problem like this, I say you will. Well, I don't know if you will, but it's likely that you'll only be given the data, as I mentioned before. You may not see the whole cross. If you're just given the data, you have to assume that the cross was done the way we said, but once you understand it, you really don't, that's okay. I mean, you don't need to go through the entire cross. You can look at the data and say what we just said. The largest numbers are going to be the parentals, etc. But it may be all mixed up. In other words, the data we looked at was 2 parentals, 2 recombinants that came from the same crossover, etc., etc. They might not put them in any particular order. The gene order may not be correct. The classes are not going to be arranged in the right place next to each other. Sometimes it's best. Well, I think it's always best, but it depends how much time you have. I would rewrite the data the way you like it, which means the way I like it. Identifying the classes that correspond to each other, and sorry about this, and identify the classes that correspond to each other, and that means, figure out who are the parentals, figure out double crossovers, and also, unless it's obvious, you need to figure out which groups of recombinants came from a crossover between one pair of alleles, because that will always generate 2 corresponding classes, and which ones came from a crossover between the other pair of alleles. It might be obvious, like let me give you an example. If you saw data, I'm just going to have some idealized data here. 1,000, 400, 100, 3, 5, 126, 409. I can't fit it, I'll put it up here, and 1027, right? You could quickly go down, and in this case it would be obvious. You'd say those are both parentals, they're present in such high number. These are both double crossovers, they're present in such low number. And in this case, it's pretty clear because of the numbers that the 400 and the 409 go together, and the 100 and the 126 go together as corresponding members of recombinant classes. If the numbers get a little closer together, it's a little harder to figure that out, but you can always do it by figuring out a crossover event between a particular pair of loci will always lead to two definable classes. Okay? Now, if you're good with all this, I'm very, very, very happy. A lot of times, since you don't know what the order of the genes is, if you have time, I would strongly suggest doing a little trick I call the flip trick. That's a way to figure out very quickly which gene is in the middle. If you don't have, let me disclaim this. If you don't like the flip trick, don't do it. You'll still get the right answer the other way. Okay? Really. But if you do like it, I like it, it's a way of making sure that you're writing out your data in the correct order so you don't have to mess with that later. You don't have to worry which one's in the middle later if you can figure it out now. And it isn't that hard to figure it out now. So let's see how the flip trick works. We have this same data again, right? And here's the whole question. Remember, I'm going to draw it out even though we looked at it again. Here's parental chromosomes. SC, EC, CV, plus, 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 right? That happens to be the right order, but say you didn't know that. Look what happens with a double crossover, you guys. We already did this, but now I want you to see it in a different way. Right? The SC and the CV stay together, and the plus and plus stay together, just like they were in the parents. But look at the double crossover classes, which come from this happening. You see SC, right? SC plus CV, and plus EC plus. You got to ask yourself, in a double crossover, the gene in the middle looks like it flips. In other words, like that. The two on the end are anchored. The one in the middle flips over. So you got to ask yourself which one flips. In this case, it's pretty clear that if you compare the parents with the double crossovers, EC is the one that flipped over. But you may say, well, yeah, I mean, you already drew it that way. Let me quickly show you if you draw it another way. I'm going to write the same exact data, just a different way. So I'll put SC, CV, EC, and plus, 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 right? We know that's not correct, but let's say that's the way they wrote it, and they gave it to you that way. Well, you're going to say, let me ask myself something. If a double crossover happened here, what would be the products? And the answer obviously is SC plus and SC plus, oh, I'm sorry. Just forget everything. Just forget that little piece right there. What I meant to say is this. Regardless of the order that they're written in, okay? What you're seeing, I'm sorry about that, but it doesn't ruin it. This is all good. This is all good. See, when I drew it, just so you know what I did, because mistakes happen and we can learn from them, honestly. You can draw it in a different way, but if you then ask yourself what a double crossover would produce, you're actually doing it as if that was the gene order. So that you can't do. But here's my question. This is the data, right? So what I wanted to say was, say they drew the data in a different order, right? So that the parentals were SC, CV, and EC, and plus, plus, plus. Keep them the same as they are, but the double crossovers now would be written, look what they are. They're SC plus and CV, but we could write SC, CV, and plus, and that's really the same thing if the order is not taken into consideration. And they're plus EC and plus, but the way we drew it up here, that would be plus EC and plus, right? So if that's the way the data was presented to you, you still got to go and say, all right, look, let's compare the parents with the double crossovers and ask which one flipped. Well, look for two that are the same. The SC and the CV are still in the same configuration they were. Even though it was drawn on the end, it's the EC that flipped over, right? So if they presented it to you in that order, you would now have used the flip trick to say, hey, you wrote it that way, but EC flipped, so it must be in the middle. Then you could rewrite everything this way with the knowledge that EC was in the middle. Now, you know, if you screwed up, it's going to come out in the end, because if you do the analysis like you have to, you're going to find out which one's in the middle eventually. I personally just think it's nicer to know before you start than to have to rearrange everything after you're done. So the flip trick, like I said, if you don't like it, you'll still be okay, but most people do like it. So in a double crossover, to summarize, the gene in the middle appears to flip with relation to the other two. No matter how it's written, as long as you keep the data the same, the orders can be turned around. EC flips in this case, which proves that it's in the middle. Okay? The flip trick. Patented. One other phenomenon. We're almost done. I know this is a lot to digest. One more phenomenon, though, that's really related to this, you have to talk about it in here, is that double crossovers, it turns out, occur, in fact, less frequently than would be predicted. And this phenomenon is known as interference. So think about this with me. How do we predict the probability that two crossovers will occur? That meaning one between SC and EC, one between EC and CV at the same time, just like we just saw. Well, it's not that hard, because there's a certain probability, which is 9.3%, that a crossover is going to happen in this region, and 10.7% probability that it's going to happen in this region. The product rule tells you the probability that it will happen in both regions at the same time. Now, if you do the math, this is in essence about 0.1 times 0.1. So it's about 1% of the time you should see two crossovers occurring together. Now, the math isn't exactly, but if you take 1% of 3256, you would expect to see something like 33 double crossovers. This is the same data. What did we see? We only saw 10. The amount that we would have thought should happen based on the distances was reduced. It was interfered with. There was interference, I. Okay? Let's understand how this happens and how to figure it out. The opposite of interference, it turns out, is called coincidence. I know that word is used in a certain way in English, but coincidence really means two things happening together. And it also means, in this case, the coincidence with our observations, with our predictions. So coincidence equals the observed amount, the number we actually saw, divided by the predicted amount. So in this case, we actually saw 10, right? We had predicted 33. If you do the math, it's about 0.3 or 30%. We saw 30% of the crossovers that we had predicted. That's the coincidence. Interference is best understood, which is I here, as 1 minus the coincidence, because whatever, in other words, it's what failed to happen, the percentage that got interfered with. So 1 minus 0.3 is 0.7. They have to add up to 100%. Out of the ones we predicted, 30% actually transpired. That's the coincidence. 70% were interfered with. That's the interference. So 70% of the predicted crossovers failed to happen, to materialize. Why? Well, it makes sense, but this is not something you might obviously think of. And again, look down here. The bottom line is, again, it's saying that these linkage groups really are physical chromosomes. The linkage groups are built on data that's not physical, but we said that they correspond or correlate with a physical distance on a physical structure, the chromosome. So while you may get into this or you may not, but it turns out we're saying a crossover happens. But for a crossover to happen, there's all sorts of enzymes that have to come and cut the DNA, paste it back together. there's a recombination complex that has a literal physical size. So it turns out, I say here, that crossing over machinery takes up space. So if it lands on a, for lack of a better word, in a chromosome and engaging in a crossover in that particular region, another set of that machinery can't fit right next to it. So it'll bounce around and move on to a less congested area. So that's why interference happens. If it's already happening in one spot, it's less likely that it's going to happen in a very, very close by contiguous spot. Because think of like, an analogy is escaping me, but it shows that there is something physical going on here, is my point. If it was just a magic little invisible scissor that went and cut and pasted, this phenomenon wouldn't happen. The fact that it's a lot of proteins and other things together shows that, put it this way, if the middle of my hand was where you wanted to make the cuts and you needed this whole machinery to make it, they can't fit next to each other, so they're going to go apart. They can fit next to each other sometimes, it's just inhibited. All right? So that's interference and coincidence. Well, I have to tell you, even for me, I love this and it is fun. It is fun. But it's a lot, especially if you're seeing it for the first time. I remember thinking it was quite a lot. So go get yourself some coffee, do whatever you need to do. Let this all sink in. If you need to look at it again, of course, that's your prerogative. Definitely try out some problem solving. And I think you'll find that you can master this concept and master this type of problem. I'll see you again real soon at another genetics session.